Alright, in this video we're going to talk about section 1.4, which is going to be building functions. So there are four operations that we can do to combine functions. They're the operations that we've been dealing with for as long as we've been doing math. We're going to have the sum, difference, product, and quotient. So we're going to assume that f and g are both functions. So these first four are very, very straightforward. The sum f plus g of x we're going to be able to find by just doing f of x plus g of x. The difference, we're going to be surprised to find out, is just going to be f of g minus g of x. The product f times g of x is just, again, f of x times g of x. And then finally the quotient f divided by g of x is going to be f of x divided by g of x. And then the one little stipulation is we have to make sure that g of x is not 0. If g of x is 0, obviously we're dividing by 0, and that's a problem. So to combine these things, let's just do a couple real quick examples. F of x is x squared, g of x is the square root of x plus 1. We want to find f plus g, f minus g, f times g, and f divided by g of x, and then state the domain of each. So we'll go through, we'll find each one first, and then we'll talk about the domain. So f plus g of x is just going to be f of x plus g of x. F minus is just going to be f of x minus g of x. F times is just going to be x squared plus square root of 1, and then for divided, we're going to get this, right? Very straightforward, very easy. Then we have to think about the domain. So if we look at the first three, we have a potential domain issue with our radical. So for all three of these, we need to make sure that x plus 1 is going to be greater than or equal to 0. So the domain for the first three is going to be x is greater than or equal to negative 1. If we look at the denominator, not only do we have to think about x plus 1 being greater than or equal to 0, we also know that the denominator can't equal 0. So for the fourth one, we want to say x plus 1 not greater than or equal to, but just greater than 0. Because if we get a 0 in the denominator, then that's going to be a problem, whereas 0 up here is not an issue because we can multiply by 0 and that's fine. So for the last one, we need to say x is greater than negative 1. Alright, so there's another thing that we can talk about called composition of functions. And that's made by taking the output of one function and putting that into the input of another function. So this little f, that's an open circle, we read it f of g of x, can be also written like this. So you would put something into g of x. Whatever comes out, its output, gets put inside of f of x. So if, again, f of x is x squared and g of x is x, or square root of x plus 1, we want to find f of g of x and g of f of x and state the domain. So the f of g of x, the output of g of x, is square root of x plus 1. So we're really thinking about f of square root of x plus 1, which means wherever we see an x, we want to put in square root of x plus 1. So we want to think about square root of x plus 1 squared, right? So instead of the x, we're putting the x, or square root of x plus 1. Well, square root squared, it's an inverse function, so they undo each other, so x plus 1. There's no domain issues here, so we can say that the domain is either negative infinity to infinity. We can say all real numbers because there's no domain restriction. Now, if we go the other way, g of f of x, the output for f of x is x squared. So anywhere we see an x inside of g, we want to put an x squared, so we're going to have the square root of x squared plus 1. So for our domain, we want to make sure that x squared plus 1 is greater than or equal to 0, which would be x squared has to be greater than or equal to negative 1. So x has to be greater than, it's not x squared, but x has to be greater than or equal to I. Since that's imaginary, this is going to work for all real numbers again. So there's no real number that's going to make this have a domain issue. So all real numbers for both domains on that one. So you've probably seen composition of functions before. Actually, I know you've seen compositions of functions before. One thing you might not have seen that's going to be useful in calculus is going to be this idea of a decomposing functions. So we're going to have to do this thing called take an antiderivative in calculus, and in that we're going to have to be able to decompose composite functions. So that's just working backwards. So if we have some function that we're calling h of x, and we know it's a composition of f and g of x, we should be able to pull apart and figure out what f and g are. So the key for this is going to be trying to find what's inside the other function. So we want to, again, we want to look for what's inside the other function. So this is usually set off with parentheses or radicals. Usually the places we're going to look. So if we're looking at this first one, we can see x plus 1 is in parentheses. We can see x plus 1 is in parentheses. So that's going to be my inside function. That's what I'm putting into the other function. So if we look at what we're called here, g of x is the inside function. So we can say that g of x is x plus 1. And then anywhere we see an x plus 1, we're going to replace that with just an x when we start thinking about f of x. So instead of x plus 1 squared, we're going to say it was x squared. Instead of negative 3 times x plus 1, we're just going to say negative 3x plus 4. And you can check your work. If you were to take g of x and plug it back in to f of x, we would end up in the same spot. So g of x is x plus 1, f of x is going to be x squared minus 3x plus 4. So if we're looking at b, again, we want to look for the inside, so we're looking for parentheses or radicals. We have a radical, so the inside, what's inside our radicals, we're going to call g of x. So that's going to be x to the third plus 1. And wherever you saw g of x, so in this case x to the third plus 1, we're going to replace that with an x for when we call this f of x. So again, if we're going to check our work, we can take g of x, plug it into f of x, and we're going to end up right here. So that's going to do it for this video, and we'll see you in the next one.